Hi, my name is Andrew McLaren, and I want to help you with SN1, SN2, E1, and E2, and really helping you understand the big picture together. There's a lot of charts trying to summarize what these things are and how they're related, but I haven't really seen one where they're talking about the mechanism primarily in that organization. And so I've done this with some tutoring students, and they found it to be incredibly useful for understanding the difference between SN1 and SN2. So I'm going to make this chart and kind of explain each part, kind of like how I did with those students. This was mostly student led with me kind of helping them out as needed. And so I'd encourage you to try and go ahead in the video and then see what I say or do and kind of fix up your model as you go along. And then I'll go over some example problems of how to actually use this now that we've got this big picture idea to solve some relatively easy example problems with SN1 and SN2 and E1 and E2, trying to figure out which one is happening, and then when those happen, what products would form. So the big picture on this is that we've got these four different types of reactions, and what I found to be really useful is asking the students which of these have similar mechanisms and how does that relate to the names? Like, what do these names mean? So we've got this nucleophilic substitution, or the SN. So you've got substitution, and then this is nucleophilic. And then the one right here, that means that it is unimolecular, meaning there's only one molecule determining the rate. So this is going to be like what we would consider like first order in terms of its mechanism. And then also it's going to have two steps to this. So there's kind of like a slow step at first, which is only including one molecule. And then there's a second molecule coming in a relatively quick step. So if you understand that SN1 is unimolecular, which has two steps, that's incredibly important because I got this flipped around a couple times when I was trying to learn this. And I thought SN1 was going to be one step, but it's actually unimolecular, meaning that this is actually when there's two steps. So you can imagine that then the two here is going to mean bimolecular. So the reaction is depending on two different reactions. So this is a second order reaction. Two reactants can affect the rate. In other words, this is all happening in one step. So everything is involved in SN2 at once because there's two molecules coming in together happening all at once. So if you can think about these two contrasted by the fact that one is unimolecular and one is bimolecular, that will be really helpful because we see the same sort of relationship here with the two here and the one there. One is unimolecular, one is bimolecular. And this means that they have similar reasoning behind them. So if you're thinking about this, it is really helpful to think like, oh, the ones here, they have a similar mechanism. Like it's going to be just the leaving group leaving, really. And so if you have something like the carbocation here, for SN1, that is going to be the one reactant. So that means that a tertiary carbocation is going to favor like an SN1 or E1 because there's a stable carbocation. So tertiary is going to be favoring like SN1 and E1 reactions. So if you have something that has a tertiary carbon, it's likely that's going to be SN1 or E1 or a mixture of those two. Same sort of deal, but the opposite way here. If you've got SN2 and E2, that means this is everything happening at once. So the leaving group has to be able to leave at the same time that the nucleophile is coming in. So this is going to like first/second order or carbocations. And so they're not so stable, so they're like kind of stable, but not really. So you can think like if I see a tertiary carbocation, that immediately tells me what two reactions are likely to happen here. And if I see one that's not, then it's going to be on the other side. So that's like the big picture on this. And you can think about how this is related to the fact that if you have a nice tertiary carbocation, it has a leaving group that pops off. Now, this might mean that there's now elimination happening, or it could mean there's a nucleophile coming in at the same time, or in the second step. So it's going to be one of those two things happening to that tertiary carbocation. So it really is kind of inappropriate to talk about this first and single carbocation being like what's being involved here. So I like to think of the word transition state as being more related to that SN2 and E1, and then the stable carbocation, preferring to be tertiary, is more like the ones. So you can think about how this is similar, but a little bit different. And in this case, the nucleophile is not involved in the rate determining step. So if you can have a ton of nucleophile, it's just not going to help speed this up when we're talking about the like SN1. If we're talking about SN2, suddenly the nucleophile is involved. And so this is going to then mean that if you've got a ton of nucleophile, the reaction can go faster, and you could even make things go to being more like an SN2 or an kind of reaction if you have a ton of nucleophile. So something might be kind of in the middle with the secondary where it's like, is it one or two? But if you got a ton of nucleophile, that might help it be more like an SN2 because you're having things pushing towards that type of reaction. So we've got these different nucleophiles kind of coming into play a little bit differently here. Um, and you can think about, okay, well, how can I then relate the E1 and the E2 and the SN1 and the SN2? So if we're thinking about the E1s, both of these are going to form double bonds. And this has to also do with this hydrogen coming off that then allows the double bond to kind of form between that and the carbon where the leaving group left. So these are forming double bonds a lot of the time with these elimination reactions. And then the SN2 and SN1, these are having a new group coming in. So in both cases, you've got a nucleophile replaces or replaced the leaving group. So we've got all this going on, and then it's like, okay, well, what happens with the leaving group? Like, what's going on with these leaving groups? So the leaving group is important for both of these, but is especially important for the SN1. So if you've got a really good leaving group, that will really help you with SN1 because it's the only thing that's really involved. So a good leaving group is going to end up favoring like SN1 kind of thing or E1 type of reaction. So we can also keep in mind that these things, they are basically both having the first step, the SN1, the SN2. So because they have the same first step, these are going to happen at the same time. And that means that this is also like this nucleophile, because it's not involved, it's okay to have weak ones. So weak nucleophiles are okay because it doesn't really matter how strong that is because, well, we've got a carbocation, this nucleophile is going to be attacking it even if it's relatively weak. Whereas here, a strong nucleophile is preferred. So if you have a stronger nucleophile with like a secondary carbocation, then it's got to be favoring like this SN2 or E2. But if it's a pretty weak nucleophile, you might have something that's more like an SN1, although those are best with your tertiary carbocations. Also, I wanted to just kind of draw in something that looked a little bit like the transition state. So if you've got this carbon, oftentimes you've got like these other like R groups or whatever. And you've got the leaving group leaving, and you've got this nucleophile kind of coming in. So in reality, this leaving group is kind of bouncing off while this nucleophile is kind of coming in at the same time. So this is a bit different its mechanism than with like an elimination reaction, which is going to have the leaving group here also attached to that carbon, but now you've got different things that are involved. So you've got this leaving group that's going to be leaving, and then you've got some sort of carbon here with some hydrogens. I'm just going to draw something kind of like that. And what we end up having is this leaving group, it's leaving, and then this is forming a double bond there, causing this hydrogen to kind of pop off as an H plus. So you can have that happen when there's a base that's present. So you can think like, okay, well now this is going to be like with a good base. So maybe let's do that in a slightly different color. So bases help with E2, and a lot of bases are going to be pretty good nucleophiles. So we want like what we call bulky bases here to help with E2. And then if you've got something that's like not a bulky base, then that's going to be a pretty decent nucleophile potentially, and that would favor SN2. So these things don't necessarily happen always at the same time, although their mechanisms are similar. Sometimes this nucleophile is like, okay, yeah, I'll take H plus, but I'm not going in to get next to that carbon because I'm too bulky or too big. So that's like a big idea that I like to think of when I'm thinking of these things and how they're similar and different. And yeah, there's a lot going on here, but if you can see how they're related through this mechanism of a stable carbocation being the only thing that matters versus having this transition state, we've got two things that are involved. That is a really helpful perspective on these types of problems. And most of the time in O Chem classes, they'll give you challenging problems, but they kind of give you hints. And on the tests, they might give you ones where it's like, okay, this really should be one of these versus the other one, and it kind of jumps out. So we'll do a couple example problems thinking about these mechanisms and those general trends, and I'll help you see how I think about those. Okay? So there's one other component that I did not mention, and that is if you have a solution that is going to be polar protic or just polar. So polar protic, if we're talking about something that's protic, that's going to be something that's possible to have H bonds. So that's going to be stuff like water, like NH3, etc. Things where you've got some hydrogen bonded to something that has a lone pair on it. So if you have something that's protic, that's going to be stabilizing charges pretty nicely. So if something is polar, it stabilizes charges generally, but polar protic is really good at stabilizing charges. So that should help you understand that if you've got like a polar protic thing, that's going to kind of stabilize our carbocation. So this ends up stabilizing that. Or on the SN2, because this isn't really a charge, it ends up stabilizing the nucleophile potentially as is. So it could be stabilizing either the nucleophile, so that could slow down like an SN2 or an E2 reaction. And then if we're talking about protic, that ends up favoring like the SN1 and E1 because that stabilizes the carbocation, making it a nice thing. So that rate determining step ends up going a little bit easier, making this stable carbocation help out this whole process. Okay, so it's kind of weird, but you can think of this as like something that's interacting with the charges, and how the charges are really applied conceptually are pretty different between the unimolecular things with an actual carbocation and then the SN2 and E2, where it's like, hey, that actually would be bad for these. So like protic is bad, and then here protic solutions are good. So they're going to make it more likely that you have a SN1 or E1 reaction if you're in that protic solution. So if we're looking at this reaction, we've got some carbons in a ring, we've got a bromine and another carbon here. So I immediately look at this and see that this is a tertiary carbon. And I know that bromine is a pretty decent leaving group. It's important to know which of these are decent leaving groups, which means that they're stable as negative ions. So I know like bromine minus there is a pretty decent leaving group because this is stable. So we can say that this is a good leaving group. And just with that information alone, seeing that it's tertiary, that should be like, okay, well, this is probably going to be the thing with the stable carbocation, which was SN1 and E1. So both of these are going to be present. This water here is not that bulky, so it can act as a nucleophile. It's not going to just do elimination. So if we look at this molecule, it could, at first, it's going to have the CH3 and a plus as the bromine has left. I've got like that Br minus. It's nice and stable in solution, and you got this plus. And now that could go one of two ways. So now you can either have the water kind of coming in, or you can have this causing an elimination. So we'll consider the SN1, and then we'll also look at the E1. So if we're thinking about SN1 here, this is going to potentially now have this water attacking this from a couple different sides. So this is in a plane, so it could be attacking from the top, or it could be attacking from the bottom here. So we can imagine that this water is attacking that and causing it to either be like an R or an S conformation around this hydrocarbon, around this carbon. So then you're going to have two different possibilities now where we've got this little house looking thing, and you could either have the CH3 up and this water kind of under. But because this is kind of a plus, you want to then have one of these hydrogens pop off as an H plus, leaving you with just OH there. And that is one of our possibilities with how we've drawn it, with the CH3 being coming towards us. And then we've got our OH kind of going back. So that's one of our configurations that we might get here from the SN1. Or we could consider it to have kind of come from the other side. So we've got the SN1, but now it's kind of not coming from, I guess we could imagine it being the bottom that we did there. Now we're going to look at this now being like the top. So like the same sort of deal, very similar sort of reaction here. But now you've got the CH3 being behind or underneath the plane, and this OH being on the other side. So you can imagine that as being a plus like we had before. And very similarly, you got something where the hydrogens come in, but it's a bit different than what we just did. So you could have that then, let's just drag this down. And this is now going to, yeah, be slightly, there we go. Slightly different because now we've got one where the OH is kind of on the other side than what it was on the other drawing that we had there. So you've got this H plus kind of popping off, and that's fine. And you're getting left with the OH that's coming as that nucleophile from the water after it gave off the H plus. So then we've got the elimination here. This elimination is going to be very similar, but a bit different. So now you've got that water, and it's going to come in, and instead of attacking the carbocation right there, you could have some water where you've got the lone pair here grabbing one of these hydrogens and causing this to end up forming a double bond here. Because you can think about the mechanism here being, because you're gonna have this carbon with like these hydrogens, and it's going to have this plus next to it. One of these carbons is going to, or one of these hydrogens will end up having that kind of come down there, And you could imagine that now the water is taking that, and you're being left with this H3O plus and the double bond. So that's two possible combinations that we got for this problem 15 here. But the SN1 has two different possible things that it might result in. So SN1 is going to have this mix because it's got that carbocation. You can imagine because SN2, it's going to have a different mechanism. It doesn't have both options like a top and the bottom. It's going to have that transition state determine which side this new nucleophile is going to be on. This is a very similar problem, slightly different, but very, very similar. So you're going to see that this is a tertiary carbocation. So I'm looking at that and I'm like, okay, this is SN1 and E1 as well. And we're going to have this thing coming in a very similar way to what we had before, but it's more appropriate to think of this as that carbocation here. Once this bromine has kind of popped off, so you can imagine that the first step is that, and now you've got this nice stable carbocation, which is now going to react with this alcohol. And so this could potentially attack like from the top and the bottom like we did last time. So kind of like what we saw last time, this is going to form like one of two things when we're talking about the SN1. So we've got our SN1s. We'll talk about that. So this ends up kind of forming a similar sort of thing. Looks very similar. But now this CH3 might be on top. And you're going to end up having now this O hydrogen CH3 with a plus on it. And now this ends up having that hydrogen kind of pop off there. So you've got this new molecule. It looks similar to the last problem that we did, but instead of having water, now you've got this new alcohol group attaching and forming, what is that? An ester. It's the other one with the oxygen connecting the two. I want to say ether. So now you've got something that looks like this. And I'm going to kind of do that to show that this is not in line with the plane of the ring, but kind of underneath it. So we could imagine doing the same thing for if this was not underneath, but on top. And it looks almost identical to what we just drew, but it's coming from the different side. Because it's SN1, you get like this mixture between the two sides attacking. I do think that this was shown as having, yeah, that being up. So we do want to indicate that in our drawing as well. And we end up having this thing looks similar, but slightly different because it's the diastereomer of this other molecule. Something kind of like that. So you get that just from the SN1's combinations, and then you can also have this E1 that can now happen. So this thing now is going to similarly react with one of these hydrogens, kind of pulling that off, because this is it's a base. I mean, it's not like the best base, but it is a base. So weak bases, like I said on that previous slide, can act as bases here because you already have something that's kind of primed and ready for that. So if you end up then having this do an elimination, you end up with should show that as kind of coming up and having that directionality I was just thinking. But this is going to end up forming that double bond like we did on that previous problem. It's very, very similar. Now one of these hydrogens is popping off and you get the double bond forming here. And so it's a very similar sort of reaction there. Now this is a little bit different, right? So if we look at this one, we can see that this carbon is not tertiary. So this is a 1,2 substitution. So I'd say this is a secondary carbocation. So I'm a little bit unsure. I'm like, okay, this maybe is not going to be like SN1 or E1 because it's not tertiary. And its leaving group is okay. Like this is an okay leaving group. but like H2O is a great leaving group. So when I look at this, I think like, oh, this is probably going to have that hydrogen attach onto the OH, and then that will be readily leaving as well. So we've got something that's a little bit tricky here. But I'm looking at this and I'm like, oh, is that? I think that looks bulky to me. I'm pretty sure that this is gotta be one of our situations where we have something that's like not a great leaving group on its own, but if you can get hydrogen on there, then it'll cause that to kind of pop off. But I don't think that this SO4 shouldn't be attaching on here. So I'm thinking that this is going to be elimination. Now the question is this in one step or is this in two steps? I think that this happens in one step, like an E1. It really doesn't really matter because this is just asking for the dehydration product. And when I see dehydration, you should see that it's elimination because that's like water is being removed in this case. You're removing like an OH and an H. So now it's like, okay, this is going to end up having this come in and potentially pull off hydrogens. But now you've got like some hydrogens here where it might be pulling it off. And then there's actually even a hydrogen right here. It isn't really drawn, but it is present there. So it's one of those two. And so you can think of it as one of the products being the double bond there, or you could think of it as ultimately the double bond here, depending on which hydrogen this ends up. So if we look at this molecule, we know that it's got a really good leaving group, indicating that it's going to be E1. Let's actually look at what that looks like though, because there's some hydrogen, now this H plus, that's kind of attaching onto here. So if we end up looking at that, we end up having this molecule that's got a plus here, and it looks kind of like that, right? So there's some hydrogens that I haven't really drawn on here, but there's some hydrogen there, and there's like 3 hydrogens there, 3 hydrogens there, and 3 hydrogens there. So this molecule is, as I said before, it's going to pull from one of these hydrogens possibly at the end here, so that you've got now the product forming where this comes in down, and then this kind of pops off to regenerate the H plus. Or you might have it where this kind of comes in like that. So there's those 2 different possibilities that we've talked about here. But there's actually a third possibility, and that's going to be a hydride shift. So this carbocation is okay, it's pretty stable, but it would be better if we could move one of the hydrogens over onto our that one over there so that we can have a plus. So instead of doing what we drew or above there, you could consider this to have a shift where this hydrogen gets brought over from there, and now it's here, and the carbocation is nice and stable there because it's a tertiary carbocation. So sometimes you can have these hydride shifts that can cause these other explanations to happen, and now possibly you could have this coming back down in there, forming like what we kind of already saw with the double bond here. Or you could have one of these hydrogens that are here, or one of the ones here, forming the double bond. So you could end up having something that looks kind of like that. So that is another possibility with this last one. So you do have to be careful. Sometimes hydride shifts can come in if you've got a carbocation that is not as optimal as other ones if you were to just bring a hydrogen or a methane group over. So you can have like methyl shifts as well. I did want to also go back and look at this problem because I did draw one of our products that's possible here when these hydrogens get targeted. There's other hydrogens here. There's like a hydrogen there. There's also a hydrogen here. So there's a couple different other options for the E1. So we drew out only one of our E1 possibilities here. There's actually 2 other ones here. So you might have something where the double bond ends up forming between the 2 methyl groups. or you might have it form where it's off to the side there. So we can end up having something kind of like this. But we've got our, this should be like in a plane. And then if it's got a double bond, it'll be like the sp2 hybridization. So it's not like a tetrahedral thing. So we can put these kind of going up and down as is. Or you like for when they're not involved in the double bond, or when they're involved in the double bond, they should be in the plane of the ring. So there's a couple different possibilities that we had on there for a similar reason. Luckily, this was a pretty good carbocation, so there's no hydride shift there though. All right, I think that that's it for me. These problems can be pretty complicated, but if you're trying to think big picture, if you've got a nice carbocation, that should be a unimolecular step. If it's not that good of a carbocation, it probably is going to then be bimolecular. And then it's a question of, is this going to be something that can act as a nucleophile, or is it too bulky to really get in there? Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.